Hi there, and welcome to the Machine Learning for Structural Interpretation section. My name is Jason Furtney. I'm representing Itasca, and I'll be giving an initial presentation here on an introduction to machine learning. So this is what I'll cover. I'll cover an introduction to what is machine learning and why is it useful and questions like that. I'll talk about and show three motivating examples that I hope are interesting to the group. I decided to give kind of a breadth of examples rather than do a really deep dive on all the details of one example. So I'll show three examples. I have another module, which I'll give later, where I do a much deeper dive on some image recognition work, which I'll describe later. And then I'll close up this presentation with a description of how you can get started with this machine learning new technology. So this is the definition of machine learning that I like. Machine learning is the art and science of making computer predictions without explicit programming. And we'll come back to that idea of domain agnostic algorithms, or these things don't know anything about structural geology or anything like that. So we'll return to that point later, but this diagram on the lower left here just broadly lays out some of the different areas of machine learning. And the two broadest categories are supervised learning and unsupervised learning. So in supervised learning, very broadly, we have some kind of task and we have examples of that task being done. And the computer is able to look at examples of a task being done and learn how to perform that task. And as more examples of the task are added, the computer gets better and better at performing the task. So we'll show some examples of that. Unsupervised learning, in contrast, is more about finding structure in data, or finding groups or things that are associated, or looking for anomalous conditions, for example. And I'll give examples of both of those. On the right, I have the rocket here. So this is just something to think about. You could think about machine learning as a high-tech rocket, but fuel is needed to make rockets go. And in the case of machine learning, data is the fuel that makes this thing work. And I'll keep returning to that. In the type of work we do, we're often in this data limited regime where we don't really tend to have a lot of data about the subsurface, but that is changing. So I'll come back to this idea of the model is the data, and that's really one of the takeaways that I want you to have from this. Okay, so why is machine learning useful? The biggest obvious thing to start with is that with machine learning, we can take advantage of this current era that we're in of big data. And the graph on the right shows world data storage over time. And it shows that we have thousands of exabytes of data under storage. And machine learning and artificial intelligence have become very successful and popular in recent years because we have this data. Machine learning models are extremely flexible, and they can learn a highly nonlinear behavior. Machine learning models are fast, and it can even just take a few milliseconds to run something. And finally, an advantage and why they're useful is that they're not domain specific to any domain. We're going to look at using generic algorithms and generic prediction capabilities in the field of structural geology, but the algorithms don't know anything about that kind of stuff. They're just generic, powerful data algorithms. So this is the first example that I decided here, and this is looking at stereo nets and finding joint sets in a stereo net. And because you've made it this far in the course, hopefully you know that stereo nets are two-dimensional projections of three-dimensional orientations, and they're often used to find structure in folds or joints or bedding or what have you. A typical thing we might do with joint sets is to contour them and look for hotspots. And you could see here that maybe there's 3 joint sets, or maybe just 2, or up to your interpretation. But this is an example of something that machine learning can do really well. So this is an example of unsupervised machine learning. We're using it to find structure in the data. We're doing what's called spatial clustering with the simplest way to get started is with this k-means algorithm. And we're saying, okay, we're going to look for 3 groups. So we have to tell it the number 3 to begin with. And then the algorithm finds the grouping of points that maximally isolates the groups from each other, or finds groups that are most likely to go together. And it does that automatically very quickly. So in this case, if we look back here, yeah, there's probably 3 joint sets. So, these are the averages of those groups. And I'm just showing a source code here just to hopefully show that this is a very easy thing to use, that it's just a few lines of Python code. And we'll get back to Python and talking about that. Here's another example. This one's a little bit more ambiguous now. So is there 1 joint set here, or 2 or 3 or 4 or more? With this joint set, we can use the k-means 3. So in that case, we're saying find me 3 groups. And it dutifully does that. But I want to introduce another algorithm here called affinity propagation, where we don't have to say the number of groups beforehand. And there's another similar algorithm called dbScan that can remove outliers and do some other things that are also useful. But just to introduce the basic concepts here. So there's a lot of subtlety to finding joint sets and so on. And there's software packages that you can buy that do that, like DIPS or what have you. And there's other subtle issues about removing outliers, being careful about near vertical joints. And you might want to search within some cone of some angle. And I'm not showing that here, but the point about this is to show you something that's familiar, introduce a basic unsupervised machine learning algorithm, and make a few points. So, the first point to make is that you could look at these and you could probably do better yourself on any one of these. But machine learning is really, really fast, and it can do thousands of these a second. And although machine learning is not perfect, it's unbiased and it's consistent. So, you might have thousands and thousands of these joint sets with hundreds of points each that have come from some kind of photogrammetry analysis or radar or seismic or what have you, and you can treat them very uniformly with a machine learning algorithm like this. And I showed the source code in the hope that it would just show that this is easy. And the point wasn't to understand each line of code. It was just to show that it's a few lines of Python code to do these kind of things. So that was unsupervised machine learning. And I'll show 2 examples of supervised machine learning now. So this is about predicting rock strength from core logging information. And an estimate of the rock strength is needed so that we can do a geomechanical analysis to inform a mine design. And then that goes into the economics of the mine, and is it feasible, and what should the mining method be, etc. So usually the way this is done is a large amount of holes are drilled, something like 1,000 holes, and it might be like 600 kilometers of core in a large project. And things like mineralogy, alteration, lithology, geotechnical, maybe assay, maybe hyperspectral imaging, maybe core photos, all kinds of data is recorded. And generally on a subset of the holes, some kind of strength testing is done. And traditionally this was UCS testing, but now it's more common for these point load tests to be done. And these are inexpensive and they're fast, but we still can't do 600 kilometers of core under point load test. It would just take too long. So what we're doing in this example here is using machine learning to predict point load strength from the information that's been logged. So all the holes are logged, and a subset of the holes have strength data. So one of the points that I'll revisit here is that the model is the data, and the data itself and getting good, clean data is very important. And it's about 90% of the effort. So in this case, we had 600 kilometers of core of data, and we had to go through an exercise of homogenizing that into 1 meter intervals, dealing with missing data, for example. And what we have are what we call raw features and engineered features. So raw features are things that are directly recorded by the logging folks. So rock type, RQD, fracture frequency, the presence of minerals, for example, alteration facies, what's the rock density. So those would all be what we call raw features. But there's another really critical step called feature engineering, or creating engineered features. And in this, we're applying our domain knowledge about geology, about these deposits, to create features. So features are machine learning model inputs, to create features which are meaningful, in terms of geology. So in this case, we came up with a mineralization and alteration index system, which is a function of what minerals are present, for example. So feature engineering is using your domain knowledge to help the machine learning model by combining kind of raw data into features that have a physical meaning. The machine learning model used in this case is what's called a decision tree. And I won't dive into all the details of how this works, but these are trees of yes/no questions. And you might think of it as, is the rock type diorite? Is the RQD less than 40? Is there hematite mineralization present? Is there chlorite alteration facies present? You answer a series of yes or no questions and you get to a rock strength. So this is an example of classification, which is a type of supervised machine learning. There's another layer to this that we have a lot of different trees, and we're combined them together into what's called a forest, and that makes the prediction more robust, but I won't get into that specifically. This is an example. So this is like a test hole where we actually do know what the strengths are, but we're trying to predict them with the model. And we haven't trained the model on any data from this hole or either of these holes. So these are graphs of rock strength actuals in yellow, and the blues are rock strength predictions. And you can see that, machine learning is not perfect. It doesn't exactly follow everything, but it is able to follow the trends and find weaker zones and stronger zones. And about half the time, it's within 1 megapascal of the strength estimate. So again, not diving into all the details of this specific example, but just trying to show what you can do with machine learning and try to put it in the context of structural geology, geomechanics. So here's a few intermediate conclusions or things to consider. So I'm just really reiterating this thing that the model is the data. So you really have to put effort into collecting high quality data. In one of these projects, about 90% of the effort is manipulating, preparing, cleaning up the data, and getting it into a format that you can feed into the machine learning algorithms. So this concept of feature engineering is really critical. This is where we take our domain knowledge as experts and apply it to this process so the model can learn better. You can't just take raw data and put it into machine learning and expect to get good results. One thing that's interesting is that the model can make a prediction, but it doesn't really tell you why it makes that prediction. So sometimes the prediction insights are a little bit limited. But these exercises show you information and trends and predictions in the data that you wouldn't be able to make yourself. So that's really the power of this thing. Okay, so that was supervised learning and classification of choosing strength classes for the rock. This is another example of supervised machine learning, and this is what we call surrogate models. And this gets a little more into the geomechanics side, but it's still worth looking at here and relevant. So in geomechanics, we use fairly complex numerical models. They're relatively difficult to set up, and they can take some time to run. And generally, you would only run a few cases. But what we're doing is we're making easier to use models that we call surrogate models. And this is a machine learning model that's been trained on a synthetic data set that we generated with a numerical model. So essentially, we're running a validated numerical model. We're generating a synthetic data set that maps some kind of inputs like rock strength or rock properties or slope height into some output like factor of safety, blasting behavior, bearing capacity, etc. And essentially, the surrogate models can quickly and accurately predict the output of a numerical model, even if it's very, very complex and even for a wide range of inputs. And they're simple enough to be run on phones, for example. So this is a movie on the left. And again, I'm not going to go into all the details of slope, stability, geomechanics, and Hoek-Brown properties and so on. But on the far left are rock properties that you can change. And on the right, on the top, is a slope design curve where we're showing lines of constant factor of safety in slope height, slope angle coordinates. And I hope what you can see is that we can change these inputs in real time and get an immediate factor of safety answer that would have otherwise taken a while to run a numerical model for. So this uses neural networks, and this is an example of a very nonlinear behavior that can be learned by these machine learning algorithms. So I want to focus on showing the concept of this learning curve here. Relating to these surrogate models. So generally, when you start a machine learning exercise, you're not going to know how much data you're going to need to make it work. And that can sometimes make it hard to get started. But the way you do this is through this learning curve. And this plot on the right shows the quality of the model as a function of the amount of data. And this is the absolute essence of machine learning here, that we should see the model quality going up as we add more data. So I want to drive home the learning curve. And anytime you are engaging in a machine learning activity, you should think about, I would like to look at a learning curve so I can see that my model is improving with adding data. And this can maybe help to give an idea of how much data you need. If your learning curve is still going up, then adding data should help your model. So just concluding, I tried to show 3 examples, again, motivating examples. I didn't dive into all the details, but I hope I can show you the type of things you can do with machine learning. A great way to get started is through Andrew Ng's Coursera course on machine learning. This is a free course. The link is provided here. That's how I got started. I've put a few logos of different software-related things on the right, but the Python programming is really kind of the center of the gravity for these machine learning algorithms. And I recommend that you invest some time in getting comfortable with Python programming. And that can lead to accessing these algorithms. I think the best way to get started is to choose a practical data set that's meaningful to you in your work and use that as a learning exercise and just get started. Use machine learning to complement your current workflow, and don't just throw everything you're doing away and do it the new way of machine learning. Do what you're already doing and try to find some ways to complement that with machine learning. And the biggest piece of advice I have is just don't be afraid to get your hands dirty. You have to just start. You have to try things. You're going to make mistakes, but just get out there and get started, and it'll really be an adventure for you. So, okay. So in summary, I just want to keep beating the drum that the model is the data, and you really have to have great data here. I showed 3 examples, and I want to hit a few of the buzzwords or keywords here. So in joint sets and StereoNet there, we looked at unsupervised learning, and we looked at clustering algorithms. We moved on to talk about supervised machine learning, and there we were trying to predict rock strength from logged information. And we used decision trees there and the random forest. So a forest is a collection of decision trees. And I talked about the importance of feature engineering, which is bringing our domain knowledge into the exercise here. And then finally, I showed these surrogate models. And these are neural networks that are learning a very complex behavior that they've learned from essentially a numerical model parameter study. And a key idea there is that learning curve. So again, if you're doing a machine learning exercise, you should always be looking at a learning curve and understanding how your model is improving as you're adding data. And then again, my biggest advice is you just have to get started. You just have to approach it with some kind of a fearless attitude, and you're going to make mistakes and get confused, but you're going to figure it out. And I really think there are a lot of applications of these types of techniques in our work. So just get started. So please post your discussion or questions to the D2L course site, or you can email this gce@arizona.edu website. So thank you very much for your attention. Again, my name is Jason Furtney, representing Itasca, and I'd certainly be very pleased to hear from you about this kind of stuff. So thank you.